Oh, hey. Hi. I think I'm live. I was drinking in my favorite cup. I was reading some articles on ZK Mesh, very interesting. But since you guys are here, let's jump into session number 3 of ZK Hack 5. I'm very happy to be with you guys. Yeah, let me know if you can hear me in the YouTube comments. Cheers to you. Maybe you'll get one if you come to one of our hackathons. More on that in the coming weeks, I guess. Let's jump into it and say again a few words about ZK Hack for those maybe who missed the first sessions. I'm gonna go through it quickly. I think maybe by now you know this map. We're gonna just go through it very quickly. The website zkhack.dev is where you get access to everything we've produced and done in the past, all the projects, the Twitter, the blog article, the previous puzzles, ZK Mesh Mini. And yeah, actually ZK Mesh, as I was talking about it, went out 10 days ago as the recap for the month of November. I mentioned last time that it was a good starting point, whether you're a beginner or an expert with zero knowledge. So this is kind of how it looks like. At the top, traditionally, we have the research paper. So that's probably a realm for people a bit more advanced. Although, this past few months, years even, we have even more like app-focused research as well. You can see here some location-related, maybe some identity-related topics. But yeah, maybe if you're more on the beginner side, you would scroll down the newsletter and check the articles. So for instance, in the latest one, we had like an interesting draft report from NIST, an institute doing the standards for cryptography about post-quantum cryptography. That's very topical, as there's been some announcement related to that lately. But you can also, there's a very nice article by ZK Security talking about the 10 must-read papers with like small summaries and stuff you can check out. Yeah, there's a whole bunch of articles, so really invite you to check it out. It's very insightful. But back to our ZK Hack map. We're now checking the YouTube part. So I guess you know about it since you might be seeing us on YouTube right now. Maybe you're watching us on Twitter as well. If you are and have questions, well, jump on YouTube. But YouTube is not only the place where we stream this online event. It's also where you can find the recordings from all our events, the hackathons, the meetups, past ZK Hack Online, and also the ZK whiteboard sessions. Since I'm talking about ZK whiteboard sessions, so that's an educational content series about zero knowledge. It's actually featured as well in ZK Mesh, by the way. In case you didn't get it, check out ZK Mesh. That's really a good resource to find everything you need that's going on in the ZK space. Jumping on the Discord now, in case you're not there, well, you should. There is like about a bit more than 5,000 members in there. We have channels for events such as ZK Hack 5. We have a dedicated channel for that. You can also find resources, and that's where the study groups happen. So if you're interested in study groups, really join our Discord. I will pause it in case you have your phone next to you and you want to join. We have the ZK whiteboard session study group going on right now. We'll have a session in a couple of days. There was a session of the Snark book just before this ZK Hack 5 week. So yeah, there are a couple things going on. The Tata book as well is well advanced. So yeah, check out our Discord. That's where the action is. And you can meet other people, whether beginner or advanced, ask questions, advanced questions as well. So yeah, make sure you join us. Last but not least for this map is the events. So we organize IRL hackathons. So keep your eyes open. We might have some announcements in the coming weeks for the first semester of 2025. We also organize ZK Hack meetups, jumping from city to city. We will have also a bunch of them in 2025. Of course, you're aware of ZK Hack Online since we're in the middle of the 5th edition. And it will actually end with a bang with the ZK Job Fair, a very fun event that we will organize for the last session of this ZK Hack 5, which is next week. So all the schedule can be found on the website. I said the schedule with really all the information that you can find. So check out the website if you didn't know about it yet. And jumping into what we are doing now and today, ZK Hack 5. That's an original creation really by ZK Hack that's been going on since COVID. It's the 5th edition, so it ends with a ZK job fair. I'm starting from the end. I will show you maybe a bit how it looks in a few slides. And it's really two things going on in parallel during the 4 weeks of the event. You have a puzzle competition with puzzles to hack, and maybe some of you are here to hear about the winners for the second puzzle, or maybe discover the next puzzle, the last one that will be unveiled at the end of this session around 7 p.m. UTC. So people compete for prizes, a bit for glory, mostly, I would say. And we also have weekly workshops. We had one with ZK Verify last week. We have Polygon today, and we'll have one with Nebra next week. Reminder, the videos are can be found on our YouTube. So at ZK Hack Dev is the name of the YouTube. So the videos, the recordings, but also all the videos, as I said earlier. So the program for today is going to be the winner's announcement for the Puzzle 2. It's been a packed week. People were quite excited. I don't think it was as hard probably than the previous one, but yeah, let's talk into the details in a bit. It will be followed by a workshop by Polygon, mostly about Plonky 3. And we will unveil the last puzzle, the puzzle around 7 p.m. at the end of the workshop as usual. For next week, we will have, well, the last winners of the last puzzle announcements. Then we will have our workshop with Shumo from Nebra. And then we'll have the closing ceremony. By that, we mean we will announce all the winner, the global winner, and all the prizes as well that the people who participated to the puzzle competition will be able to get. Last but not least, really the last thing for this series of events is traditionally a ZK job fair and a digital after party really. So we will share the link of this after party during the last session, so next week. We will share it in YouTube, also on our Discord. So make sure you're here or there to be able to join us. It's going to be fun to talk about maybe other puzzle participants, the people who watch the workshop with you, and also meet, of course, our partners team who helped made the event a reality. So here's a sneak peek of the sponsors booth. So this is where you will be able to interact with the partners. So ask them questions, of course, about what it is to work in ZK, maybe tell you a bit more about what they're working on. And I hope also maybe you will be able to talk about the open positions for jobs that they have published on the jobs board by our media partner Zero Knowledge FM. So you can already check it out if you want. There are also other jobs from previous posts from other sponsors and other participant people in companies from the ZK industry really. So check it out. There are a bunch of them on there. We're sharing all these links as I'm speaking on the YouTube comments. So yeah, if you're on Twitter, feel free to jump on YouTube as well. Maybe it's a good way also to ask questions directly. But you can find all the links on the YouTube channel as well. So ZK Hack 5, Puzzle 2. Let's jump into it. I will bring Nico from Buying Capital on stage to talk about the puzzle. Hi, Nico.
Hello, Gaylord. How are you?
I'm good. Thank you. Thank you. I can see, we have a nice audience and people to talk to about this second puzzle. So yeah, tell us more about the intricacies and mysteries of this second puzzle.
Yeah, so don't look up. In this puzzle, we're combining a lookup argument with small fields. And those are two techniques that are used to make our snarks faster, usually. But here in this case, when you combine them together, something breaks. So the lookup argument was sort of a very simple version of logup. And I really recommend watching Ariel's whiteboard session. I think that's module 3 on the topic.
That was hint number 2, actually. Hint number 2 was watch the ZK whiteboard session.
Absolutely, it was a hint. And in the session, actually, Ariel brings up, here's a condition that we need to meet for the protocol to work. In this case, the condition was our field needs to have a characteristic that is big enough. So what does that mean? I'll leave it to the write-ups because I think the write-ups explain this super well. But the idea is when you multiply something by the characteristic of a field, you get 0. Or in other words, if I add something to itself that many times, I get back to 0. And that was sort of the key to breaking this challenge. To pass the challenge or to break the puzzle, you had an equation you had to check. It was a sum equals another sum. And so one side of the sum you could set to 0 using this M vector that was part of the protocol. And the other side of the sum you could set to 0 by adding something to itself many, many times. And this number of many times is this variable P that we had in the code.
So this was related to the small field to the small field aspect, maybe.
Exactly. It is because we're using a small field with a small like characteristic, essentially. So if you're familiar with things like Binyas, in that case they're using characteristic 2. So in that case it would be very dangerous to use logup. You can use other lookup arguments.
Okay, nice, very interesting. We also have a whiteboard session on small fields, actually.
Yep. How convenient.
Yeah, exactly, very convenient. So if people want to understand more about these topics, they should watch both of the ZK whiteboard session. And while they're at it, you should watch the whole series, really. That's very educational. Thank you, Nico. That's very insightful. I think now we can jump to the prizes. So let's look into who won, who was the fastest really to crack the puzzle. So reminder, we have like a USDC as prizes for the people who are the fastest to crack these puzzles. We also have a prize for the best write-up. We will finish with that. So that's basically for every puzzle, we retrieve all the people writing an explanation about how the puzzle works. Pretty much what you explained, basically, but as a write-up, as an article, and we select. The puzzle team select the best one, and they also get a reward for that. So let's get to the announcement. The winners of Puzzle V2 are at the third place.
Constanza. Congratulations, Constanza.
Congratulations. At the second place, we have
Damian Strasak. Sorry. I hope I mispronounced your name. I'm sorry about that. But congrats, Damien.
Yeah, congrats. I think it's our friend from Aleph Zero, actually. So it's fun to see familiar face in this on the podium. And the fastest to crack Puzzle V2 is, drumroll,
Team Zelik. Congratulations, Zelik.
Great.
Also
well done,
familiar
guys.
name to
Exactly.
ZK Hack.
Exactly. Yeah, it was. I think they ended up second at the last edition of ZK Hack. So it's also a reminder that people can actually participate as a team. So I think on the ZX side there are 2 or 3 people, if I'm not mistaken. This is completely fine. We're cool with it. So yeah, FYI. And before we move on, the best write-up goes to
Neos Ledger. Congratulations.
Yeah, another familiar name. Because he was the winner really of the puzzle last week. And as you can see, we have actually 3 new people who did in the top 3, who made the top 3. So you can check the leaderboard on the webpage. As always, I'm sending it. So it should be uploaded in a couple minutes. You will be able to check it out yourself. But here is a sneak peek. As you can see, we had some moves at the top of the leaderboard. So Neos actually was first last week. He went down to the third place. We can see the top 3 of this week puzzle kind of went up. We can see Constance here, Damien as well, and Zelik team just here at the 4th place. All of that to say that the competition is raging. It's a thrilling competition, and we're really curious to see who's going to make it to the top next week. So yeah, here's a meme for the leaderboard of ZK Hack 5. It's also a good reason, I guess, to jump on the Discord, maybe ask Biko Moves itself how it feels to be at the top of ZK Hack 5 leaderboard. Thank you very much, Nico. I guess maybe I'll see you next week for the last puzzle. Thank you again for the insights, and see you soon.
See you soon.
Before we jump to the workshop part, I wanted to say a big thank you to our workshop partners. Again, they're really the ones making this event a reality. They are, doing the workshop, so they're really participating in the event. So we had ZK Verified. Thank you guys for the next week workshop. We're going to welcome Brian Seong from Polygon right now in a minute for Polygon's workshop, and we will have Shumo Chu from Nebra next week. Thank you very much to our workshop partners. We also want to say thank you to our community partners, so Xion, ZK Pass, Ferma, and Powder. You will be able to meet them actually I was about to say in person, but yeah, it's going to be an online job fair next week. We're going to share the link for the job fair during the workshop, during the session next week. So make sure you join us on Discord or on YouTube, and you will be able to ask them questions and just have fun at the after party. It's always a fun event where the participants and the sponsors can interact with each other. Thanks as well to our media partner, Zero Knowledge, who is hosting notably the jobs board, where our sponsors are posting their job openings. Another reminder that the videos are all available on the ZK Hack Dev YouTube channel, so check it out. We will publish the standalone video for the workshop tomorrow, but you can find the live right away, a few minutes after the session is ending. If you have your phone nearby, make sure you follow us on X. You can also, hit us up with questions if you want. We'd be happy to answer there. And also join the Discord. We have this dedicated GK Hack 5 channel for all, questions related to either the puzzle competition, but also the workshop. So join us there. It's fun, I promise. Thank you to the team who put the event together. So on the ZK Hack side, Anna, Quentin, and myself. And thanks to the puzzle team as well from Bain Capital, Kobe, Andrea, and Nico. There's also Grishta, actually, who participated to the third puzzle. So more on that at the end of the workshop. But yeah, thank you guys. And we'll make sure to add Grishta for the next session. Okay, great. So we will now jump into the workshop by Brian from Polygon. He's going to talk about Plonky 3. So let me bring him up. Brian, you ready? Let's go. Hey, Brian.
Hello.
How you doing?
Doing good, doing good. Am I audible?
Yeah, I hear you well. Please in the chat let us know if there's any issue, but I think it should be all good. Ready to talk about Plonky 3?
Yeah, let's dive into it. I'm all excited.
So can you share maybe your screen? I will switch the screen so that you can take over the presentation. Okay, we get audible AF in the comments, so I think it should be pretty nice. Okay, I'm gonna switch the screens. Here you go.
All right.
So yeah, again, maybe just stopping you before you start. If there is any questions, guys, feel free to post on YouTube. As soon as Brian, find the right time, he will maybe take the questions that are popping up. We want this to be interactive, so really don't be shy. There is no dumb question. Please go for it. And yeah, Brian, on your side as well. If you need anything, I'm going to be in the background, so yeah, feel free to ask if need be. So, and now, yeah, it's your turn. Leaving it up to you. And yeah, see you in a bit.
All right. Thank you. All right. Well, super excited to be here. My name is Brian. I work at Polygon as Senior Dev Engineer. And today I'll be presenting a little bit about Plonky 3 and also just kind of dive into a hands-on example, which is range check, which we use extensively in our modern ZK inventions. Like one of the crown of jewels is the ZK VMs, right? They can't live without range check. So we're going to dive into how to implement that using Plonky 3, and then just touch a little bit of different types of ranges so that you can understand how to optimize your constraints so that you can generate your proof as fast as you can. All right. So Plonky 3, as you all know, it started way back in the day, starting from Plonky, and now there was Plonky 2, and then now there's Plonky 3. Each one of them, it's quite different from one another, but its all goal is to serve as sort of this sort of framework or backend that people can just kind of build on top of, where we provide the prover and the verifier, and people would just need to write their constraints or circuits to write their ZK applications. So for Plonky 3, what sets us apart from Plonky 2 is that Plonky 2 was primarily engineered around a few Goldilocks, and it supported recursive proof generation, and that made it ultra fast and fast only around the Goldilocks field. But later down the road, there started to have more fields introduced to the public, such as Mercine 31 and some of the other ones as well, and different hash schemes as well. Like it was Poseidon 2, and there's Blake, etc. So In order to support all of these in Plonky 2, it means it will has to, because Plonky 2 is so well optimized around Poseidon and Goldilocks field, so it made it really hard to kind of just take out one of the components and then plug the new schemes inside. So instead of doing that, we decided, hey, you know what? Why don't we build this sort of a modular ZK proofs toolkit, which we call Plonky 3 now, where developers can choose their own fields, they can choose their own hash settings, and some of the minor settings as well. There are some PRs who are even trying to implement stir in Plonky 3. So to make this kind of a modular toolkit where a developer, depending on their applications, they can choose their settings to make a ZK applications that suits their needs. So that's Plonky 3. Basically, I would say it's a toolkit for designing custom ZK proof implementations, and that can be used to power application optimized ZK VMs, ZK EVMs, etc. I usually use an analogy, say, it's kind of similar to PyTorch, TensorFlow for building AI models, whereas Polygon Plonky 3 is there to help build ZK proof systems. So it's sort of that toolkit or framework. There's a lot of, so there is this tutorial, it's called Plonky 3 Fibonacci, and this is where we kind of talk about, how Plonky 3 works in a glance. Like a TLDR version, and then showcase how to write a simple Fibonacci constraints in Plonky 3. And what we're going to be diving into, it's a range check example. And this is where we're going to talk about the range check implementation and some of the key, idea when designing a constraint, which is, something called intermediate variables. So we're going to all talk about that today. But just quickly go through the TLDR of Plonky 3. How does Plonky 3 work, right? From developers' perspective who are using Plonky 3, the main steps that you need to work on is the top two parts, where you need to define your algebraic intermediate representations, which we call the air constraints, and also be able to, just fill in an execution trace where constraints can which we also call them as witness, right? The execution trees, which can feed into the constraint, and then we use that to build the polynomial. And with that polynomial, we start do the polynomial commitment schemes and generate proofs, etc. All that stuff happens in Plonky 3. So as a developer, you don't have to do too much on that. All you need to really define is the constraints and generate an execution trace, which we can throw it into Plonky 3, and Plonky 3 will help you figure out the rest. Yeah, it seems very complicated. I don't understand half of the steps, but yeah, only step 1 and step 2. So let's take a look at this sort of, the process of, process of Plonky 3 generating proofs in a diagram. So first off, we need to define our program, which is, if it's a Fibonacci, then you need to define your Fibonacci programs, as in, how is it going to execute? What are each steps? Is there a for loop? All that stuff. And then define your air constraints, which we're going to talk about in a bit. But basically means like it's defining the constraints where it needs to satisfy certain conditions for certain computations. And execution trace, basically, it's sort of the computation process. It's recording of the program's execution progress. You're recording the key variables within that clock cycle on those clock cycles. We're going to talk about that in a bit too. And then the rest will be just Plonky 3. So you choose your own field, you choose your own hash. And then once you have these configurations set up, then some of these ZK system setup is more of a template, but you can also customize it to your own needs. And last but not least will be prove and verify, which is like 2 lines of codes. So let's quickly take a look at what are some of the fields and hash currently Plonky 3 supports right now. So here are some of the fields that we support. Includes the Goldilocks field, Baby Bear field, and etc. Machine 31, I think it's our latest supported fields. With that on top, we also have other hashes that we support, which I listed here. And if you want to take a look at some of the deeper examples, here are some links so you can take a look at it. But yeah, this repo it's under Plonky3 _ Fibonacci. Yeah, maybe I'll share it later. All right, so that's just a quick run through of Plonky3 and overall as a developer, what is it that I need to play with? What is it that I need to really work on to make my ZK program working using Plonky3? So let's now dive into an actual hands-on session, right? So this is going to be the range check implementations, and today we will primarily going through 3 examples. One is about the Mersenne 31 range check. We're gonna check whether a number is within the Mersenne 31 range, and then also we're gonna implement another example, which is checking whether a number is within baby bear field range. And we're not going to talk about the Goldilocks, but it's pretty much very similar to how baby bear range check is done. But this V1, this baby bear range check V1 example that we will be showcasing, it's not an optimized version. So in V2, which we'll be talking about as the last example, this will be the optimized version of the field range check for baby bear field. And then during this process, we'll talk about the intermediate representation of that. All right. So let's talk about range checks. So why do we need range checks? Range checks are fundamental operations in zero-knowledge proof systems. So because in zero-knowledge proof, we don't use greater than or less than, those kind of operations to check whether a number sits within a specific range. We have to use equal signs because that's how we built the circuits. So in order to do that, we have to use this sort of a technology called range check. And during this range check, what we do is essentially, if given a number, we break down the number into binaries. And then using those binary bits, we compare, say, hey, if a number is is less than certain bits, we make sure that the top parts of the bits are equal to 1, then the remaining should be 0. Something like that. This is sort of the idea that we're using, the bit decomposition. So we're going to talk about that in a bit, but yeah, that's the overall essence. Using equal sign to compare whether a value sits within the range or no. So some of the applications include, the privacy-preserving financial transactions, secure voting systems, and etc. So for this example, let's first start with the Mersenne 31, the simplest implementation of this entire tutorial series. The reason why it's simple, you will see it in the bit decomposition form. All right, so let's first dive into Mersenne 31 range check. So Mersenne 31, if you take a look at its prime field, it's 2 to the 31st minus 1. So this is the biggest number, which this is what we want to make. Let's say given a number, we want to make sure a number sits within this range. So yeah, the range check ensures that the value it's less than 2 to the 31 minus 1. And for this example, we'll be using field Mersenne 31, and hash will be KCAT 256, and then PCS will be circle PCS. We'll talk about this Plonky3 setting in the code in a bit, but let's first get into the execution trace and the constraints. If you recall, in this part, I mentioned all as a developer what we need to worry about is defining the error constraints and the execution trace. So that's what we're going to be doing. All right, so let's start with the execution trace. So we're using 0th row, and this is the execution trace. It's basically 4 by 32. So it's 0 all the way to 31, right? So it's 4 by 32, so 4 rows and 32 columns. And we're using 0th row as the row to store the number to be checked. So let's say if there's a number that we wanted to check, what we're doing is we're breaking that number down into binary forms. So that number has to be U32, right? And then we're throwing that U32, we're breaking down that U32 number into binaries, and then we're throwing each bit into the 0th row of this execution trace. So yeah, it is stored in bit decomposition form, in big endian format. You can store it in other formats as well, but it's just, this is the way that I'm using it. And the rest of the rows, we're filling it with zeros. The reason why we have 3 extra rows is because for our Circle PCS settings, Plonky 3 does require more than 4 rows. Yeah, basically these are just empty rows. We can kind of just ignore for now. Right. Then, so we see how the table looks like. It looks like this. Then we just need to fill in the data so that we can actually represent that table in a vector, in a matrix. So this is the execution trace generation function. So the idea here is we're creating a vector that has the exact numbers of elements of total elements of this execution table. So this execution trace table, it's 4 by 32, so it's 4 times 32 amounts of elements. So that's gonna be 128. So now we have a one-dimensional vectors, and what we're doing is just we're filling the vectors with the values. So yeah. Say we're giving a number, a value, and then what we're doing, we're breaking down the number into binaries. And yeah, this is just breaking down the number and then compare with 1. If it's 1, then you push the 0, push the 1 in. If you compare the bits, if it's not 1, then you push in the 0. So on and so forth. After you finish the first row, that's gonna be 32 elements, and then you fill in the remaining elements with zeros for 3 rows. So that's going to be 3 times 32, and then you're just pushing in 0. Just be mindful, you're not pushing the actual number 1 and number 0. What you're pushing in is actually a field value. So all the number that lives within this execution trace is actually field values, not actual values. So just be mindful. So you want to push in the field values here. And once we have, pushed all the values in the one-dimensional vector, what we're doing is we have this API from Plonky 3 called row major matrix new, and you throw in this one-dimensional vector and then just specify the width of the row, and it will convert this one-dimensional matrix into a 2-dimensional execution trace matrix that is usable for when generating proofs. Right.
Hey Brian, sorry, I'm jumping on stage because we have a few questions in the background. So
yeah.
I was thinking maybe we could take them backwards, because we have one from Philip about the bit decomposition. Yeah, maybe you want to cover this one.
Oh, but the bit decomposition is not part of the circuit constraint. Yeah, it's not part of it, and we will verify that bit decomposition is done correctly in the constraint. Otherwise, you can throw in any numbers, right? If you throw in any numbers and if you're not verifying whether the original value is not matching with the bit decomposition result, then yeah, there's no point of generating the proofs. So we'll talk about that in the constraints. Yeah,
Okay.
that's a good point.
Okay, cool. I have also a bunch of questions maybe that were more related to the first part, but maybe let's tackle them now. So we had this one from Laurie.
Is Plonky 3 aimed at customization, or are its implementations also faster than Plonky 2? I think it really depends on your applications. Say if your application focuses more on recursiveness, then Plonky 2 is definitely much faster because we support this. But also that comes with a sort of limitation where we have to work with the Goldilocks field and the Poseidon hash. But now that we have like Poseidon 2 hash, which is even faster, and with Mersenne 31, and also with circle PCS, basically a circle PCS. So all of these combined together, for some applications, Plonky 3 is actually faster, but it doesn't have a recursive scheme that comes with Plonky 3. So as a developer, if you want to build on top of such setting, then you will have to write your own recursive circuits.
Okay, actually, it's funny because it relates a lot with this question from Alvaro around pretty much what you're saying. Does that make sense?
Doesn't mean it was based on Plonkish arithmetization while Plonky 3 focuses on there. Yeah, so for Plonky 2, I can't recall too much details, but I guess, so for Plonky 2, what we supported is we actually provided people to write circuits instead of constraints. So there's also a synthesization portion where you have to synthesize the circuits into constraints. But I can't recall exactly what kind of constraint that Plonky 2 was using. But it's probably not air. If it's air, then the migration from Plonky 2 to Plonky 3 would have been much easier. But it's some other scheme. Yeah, hopefully that kind of partially answers your question. But
let's check it out. And that's typically the type of discussion we like to have on the Discord. So that's something we can check out. Okay, I'll jump off again. Maybe I will jump back in case I see some interesting question in the chat, so you can focus on your presentation, and I'll be back in case we have some questions. So leaving you back to it.
Yeah, I see in the comment section someone's helping out too, so I really appreciate it. Yeah. All right, so where were we? Yeah, so to come back, I think it was Philip mentioned this. So this is exactly indeed an important piece of constraint that we need to write. So now that we wanted to build a constraint to make sure that the value, so there are several things that we need to make sure. So first off, we need to make sure the most significant bit is 0. Why are we doing this? Because if we take a look at the execution trace on the first row, this is the largest value that we have fit in already in this execution trace, and you can see the very first column is 0 because the number has to be 2 to the 31 minus 1. So yeah, just making sure as long as a number is doesn't use this first column as 1, then it should be within that range, right? So that's why we're making sure we need to make sure the most significant bits in here is 0. And then second, we need to make sure each bit that the program has fit into the execution trace is either 0 or 1, because we want to make sure the number that is representing is indeed a bit decomposition. It's not using some random values to fake the system. So yeah, this is another constraint that we need to make sure. And then thirdly would be we need to reconstruct the value inside the circuits to make sure the value matches the inputs. This does sacrifice the privacy portion, but for this example, this is how we are doing it. Otherwise, we'll have to do the bit decomposition inside the constraints, not what we wanted for this example. So reconstructing value to match the input, and the input in this case, input in this case is basically a public circuit input. You can think of it as that. And what we're doing is we're basically, by converting this binary forms of numbers into U32 again, and then compare it with the public input. And then optionally, this is just for the sake of showcase how to use Plonky 3. We're also going to make sure the sum of the remaining 3 rows is 0. There isn't much point of doing this, but yeah, we're just doing this to showcase some of the APIs. All right, so this is the constraint. It's pretty short for this example. So what we're doing is we first need to define the public struct of this air constraint. Yeah, it's just a Rust API. You using public struct, and then you have your own name. Name can be anything. And then this is where you define your public inputs for the constraints. And you feed these inputs in when you're instantiating the constraint instance. We'll take a look at how to instantiate in a bit. So this is the value, and this will be the number to do the range check. The reason why we're throwing in, again, is to compare with the reconstructed value. And here, we also need to implement a trait called base error. And inside here, it has a function called width. So this is sort of that, during this proof generation process, it needs to know what is the width of the execution trace, and this is the API that we need to provide the exact value. So 32 is the width of our execution trace. And here, this is the constraint part. Where we need to implement this error trait, and inside here, there's an API that you need to overwrite called eval. And builder basically is sort of this iterator that we will be accessing. So builder, what it's going to return, the first row, what is returning is the execution trace, the current execution trace itself. Where are we, which row are we on in the execution trace? And then if you do use this row slice API and pass in the 0th index, it's going to give you the current row. And then if you give the number that's after 0, which is 1, it's going to give you the row after the current row. And of course, you can also access this via the subscript format, just like how you access matrix. But yeah, this is a very clean way of accessing an entire row. So you're accessing the current row and the next row. And so let's go through the constraints part. Now we're actually going to go through the constraints. So here, in Polygon 3, Builder has several APIs, and some of the most used ones are called when first row, when transition, and when last row. We don't have when last row in this example, but when first row, what it does is saying, hey, if the current row that we're on is indeed the very first row of the entire execution trace, then we're going to run this constraint. Say then if we're on the second row, then this constraint is not going to be applied. So what we're checking in the first row, we want to check if the 0th bit, the 0 column of this row is indeed 0. Right? This is the very first constraint that we are checking. Right? And then now we're going to check each bit is either 0 or 1, and then also reconstruct the values. So we initialize a reconstructed value by giving it a 0 expression, number 0 in the field of expression, and then we also this is just for the next step, the optional part. So we'll talk about this later. Yeah, so first is we access the current bit. Say we are using a for loop to access the bits in every bit in the row by doing this, and then we need to make sure that whether this bit is indeed 0 or 1. So assert bool is going to give you that sort of a result where if a bit is not 0 or 1, if it's 2, if a value is 2. Then this constraint is going to fail. And as simple as, and now it's just basically just adding it. We're doing a bit shift, etc. Add it to the expression, and then add it to the reconstructed value, and iterate that for 32 times, and then we should have the reconstructed value. And last but not least, we're going to compare the reconstructed value with the public input that we have provided in here, the value. And like I mentioned, since all the values that lives within execution traces field expression, so you do also have to use this API to convert the value into a field and then compare from field to field. It's not possible to convert field to actual U32 numbers, but the other way around is possible. All right, so this is when first row. So with this only, our program should suffice already. Like it should serve the purpose of be able to prove whether a number sits within Mercine 31. But But just to showcase the when transition API, we'll also check additionally on the sum of the remaining 3 rows is either 0 or making sure they're all zeros. So what we're doing is we're creating a new sum variables, and here, instead of adding the current row, we're adding the next row's values. So let's say if currently our iterations say the current row is here, then what I'm going to be doing is adding the values of the next rows. And when I'm on this row, then I'm going to add the values of the next row, which is this row. And that's what I'm doing here is basically accessing the bits and then add them to this variable here. And then what I'm going to be doing is I'm going to check whether if the sum of the next row is indeed equal to 0. And you might notice some slight difference between the when first row and when transition. So what is going on is when transition happens when you're on, let's say in this example, when transitions happens when you're currently on the 0th row, first row, and the second row. It's not going to happen on the 3rd row. So when transition means is basically, hey, I'm currently on this row, and when I'm transitioning from this row to the next row, which means if there is a next row, then when transition will apply. And at the last row, if you want to do additional constraint checks on the last row, you can use when last row, or in this example, how I'm doing is I'm using the next row, which is the next row from the current row to check. So yeah, so because of that, this constraint is only going to be applied once when it's on the very first row. And then after the first iteration, when it comes to the second row, it's not going to run this constraint, and it's not going to run this constraint. It's only going to run the when transition constraint for 2 additional times. So for the first time, it's going to run 2 of these together in the first row, and when the iteration goes to the second and third row, it's only going to run the when transition constraints. So yeah, that's sort of the constraint part where now we have the execution trays, and then we have the constraints. So from developers' perspective, the code that they need to write is pretty much done. All that is left is to write the configurations of Plonky 3. We'll just quickly dive in, but not too much because I don't think we have too much time for that. But yeah, this is sort of that template that we have provided. Most of the time, you don't have to change too much of this setting. But as you can see, what we're using in this, this val means the field type that we're selecting for the Plonky 3 backend. So I'm just choosing Mersenne 31 because we're checking the Mersenne 31 range check, but they don't have to match. It's just an example. This could be some other field. But just in this example, I'm choosing Mersenne 31 for the field for the Plonky 3 backend. And then for the hashes, I'm using catchat 256 hash. And if you take a look at, and the remaining, it's some of the setups for the fry prover, the fry configs, which will be thrown into the start prover. And as you can see, we can also specify what type of PCS that you wanted to use. In this case, we're using Circle PCS. So this is sort of a brief info, but if you wanted to dive into a deeper look of some of the other implementations, you can go to plonky3/plonky3 repo, and then there are 2 examples that we have showcased so far, which is the catcat air. There's also Poseidon 2 air. And if you go into these, then you will be able to see these examples are basically the configurations of different fields and different hashes, along with different polynomial commitment schemes to run the same constraint. Right? This is basically a constraint of checking whether a catcat hash is done correctly. And for that same constraint that you have written, you can run it in different settings, and you can test them out in 1 line of code. So it's pretty handy. All right, yeah. And so now that we have this, so until this point, this is where you have all of the configurations for Plonky 3 from line 77 all the way till here, line 120. And now that you have your Plonky 3 set up, all you need to do is first you instantiate your air constraints, right, which is via this. This is our constraint that we have written. This is the value that we're throwing in. And then this is the execution trace. We're also providing the value here so that it can generate the execution trace correctly. And then last but not least, we have Fiat-Shamir scheme, which is generating a sequence of challenges for both prover and verifier, the same set of sequence. And then one lines of code to generate the proof and another lines of code to verify the proof. So this is sort of just a high-level overview of a simple Plonky 3, prover setup, and then how to verify it, and also how to write your constraints, execution trace, etc. All that I've written it in this example. Right. This is the constraints, and then this is the constraints implementations that we talked about, and then this is the execution trace, and the rest is basically the Plonky 3 instantiation and running the proof and verify. All right. So now we'll talk about the next step, which is the baby bear range check. Before that, why don't we kind of talk about how it performs? This is the outputs. But be mindful, this is a command for running it in a dev mode. It's not a production mode. You can also specify it with different flags. By default, it's running in dev mode. And what we're doing right now is we're providing the value 100. And what it's going to do is going to generate the proof for 1.37 seconds. Yeah, be mindful, this is the dev mode, so it's a little bit slower. And it's going to verify in 5.8 milliseconds. So all these outputs is going to be showcased when you run this exact command. The code is available here, so you can take a look at this repo and then download it and try it on your local server, local computer. And now we're also going to test it with the max value of Mersenne 31, which is this value, the 2 to the 31st minus 1. And it's also going to go through. So the proof is going to work, and then the verify is also going to work. And last but not least, we're going to test it with an overrange value. So this number is more than what it's bigger than the Mersenne 31 field. And if you try to run it, it's going to fail in proof generation process. And as you can see, it failed at an assertion of left equal right. It's because this number actually has the most significant bits of the execution trait, the 0th column. It's set it as 1. So it's going to fail at that exact constraint, the constraint where it's checking the 0th column is 0 or 1. As you can see, it's 1. It should be 0. So that's why it failed. All right, so that's for the Mersenne 31 example. The general, I think for the very first example, what I'm trying to really achieve here is to get an intuition of what range check is, and also from range check we understand how to, how to instantiate and write your Plonky 3 program, all that stuff, the constraints and the execution trace, etc. Now we'll dive into just a little bit more complicated example. It's called the baby bear range check. It's not as simple as just checking the very first bits of the number, because the range of baby bear range looks slightly different, slightly more complicated. So yeah, we'll dive into it. And just so you know, each of the examples that I'm showcasing here, their Plonky 3 setting, they're all different from one another. I'm only doing this to showcase different, settings that you can apply for the same constraints. You can also try that with, you can also just try to change it on your own. But yeah. So first, let's talk about baby bear range. So baby bear range compared to Mersenne 31, it's a little bit more complicated. It is a number that looks like this. It's 2 to the 31 minus 2 to the 27th. It's also a 32 bits prime, but the range, it looks something like this. If we represent this In a binary form, it would look something like this, where you have the most significant bit, it's also equal to 0, but you have the very first bits to the fourth bits equal to 1, and remaining should all be 0. This is the largest number that Baby Bear field can represent. So without further, I guess I don't have to mention too much. Now what we're going to be doing, pretty straightforward, just like the Mercine 31 example, we'll be writing our own execution trace function and also the constraints. So let's dive into the execution trace. We are breaking down the number into binaries, and then we're throwing it into the one-dimensional vector, and then convert it into a matrix. And just so you know, the PCS we're not using circle PCS, and this 2-digit-fry PCS doesn't have a requirement say you have to have more than 4 rows of execution trees. So that's why we're able to do it in one-dimensional. For constraints, let's go through the requirements. So first, it's the same thing as the Mercine 31. We need to have the most significant bits as 0, and then we need to check whether if the bits from first to the fourth are all 1. Like we need to make sure we need to check whether if all of them are 1 or everything else, right? Because that's only what matters. And then thirdly will be check if the remaining, sorry for the typo, check if the remaining bits are 0. So this happens if the second constraint is true, right? Then the remaining has to be 0. Otherwise, like if we take a look at here, if the third column here is 0, then the remaining columns from the third column to the rest can't be anything. And also saying, like the only hard requirement is if the first bits to the fourth bit, they're all 1, then the remaining from column 5 to column 31, they all has to be 0. Otherwise, it's going to be more than the Baby Bear range. And then the usual stuff, we're going to check whether each bits are 0 or 1, and also we're going to reconstruct the value to match the public input. All right, let's dive into the constraint. So this is the public input, and we have the execution trace width. Now we dive into the constraints. So we're accessing the very current row, and using this current row, we're going to check the very first condition that we have mentioned here. The most significant bit is 0, and that's what's happening here. Right? It's trying to check whether the 0th index, 0th column of the current row is equal to the expression 0. And this is the inefficient way, which we're going to talk about the efficient way in V2. So what we're doing is we're basically multiplying the first column element to the fifth column element, to the fourth column element. And yeah, we're just trying to get a product of it. And this is that value. And then for the remaining, what we're doing is we're just adding all of them together from the fifth column all the way to the 31st column. We're adding them together and we're storing it as this variable here. And what we're doing is there's a when API. So when API is sort of like a Boolean sort of an API, when this is true, when this is false. And because this is 1 or 0, we can use it this way. What we're going to be doing is we're going to check whether if the upper bits product, this value, which is the product of first column to the fourth column, if it's equal to 1, which in this case, when would means when true, right? And then it's going to check assert 0. Is trying to require the remaining bit sum equal to 0. All right, so that's sort of this magic that we're doing. The second and the third constraint, we're having all of them in this one line of code. All right, and the remaining is basically making sure every bit is 0 or 1, making sure every bit is 0 or 1, and then we are adding the reconstructed value and then compare the reconstructed value to the original value. Same thing that we did in Mercine 31. All right, so now that we have done our constraints, what we're going to be doing is, also, of course, prove and verify. So same thing, we're going to test it with a simple number called value 100. Just so you know, there's a little, there's something that we are going to talk about in the later V2 version. But something that what we have also changed our fry config in the code. There's something called a lock blow up factor. This is basically a result of, because we're doing multiplications of I guess like of the different variables in the constraints, and which makes the interpolation process way more challenging. So we need to add, and which is going to, and the more, maybe it's better to talk about it in the later section. But yeah, we have to add this number from 1 to 2 because we have a degree 4 constraint in our current constraint. Degree 4 is because we have 4 variables multiplying one another. So we call this a degree 4. If there's 3 variables multiplying with one another, then it's degree 3. And the constraint degree and a log blow factor, they're sort of interrelations of 2 to the n. But yeah, just be mindful of this. We'll talk about it in detail in the later V2 section. And because of this, the overall resource that it requires and also the computation complexity is gonna be it's gonna rise as well. So yeah, that's why we say this is an inefficient constraint. But nevertheless, let's still run it. The value that we're throwing in is 100 for this for the first test, and this should come out as looks something like this. It has a verify 1.41 millisecond. The proof is 9.11 millisecond. And for the panic, if you're curious, you can take a look at this. But if you run it in the production mode, then it's not gonna, showcase this panic message. It's mostly there for debugging purpose. And if you want to run it in the production mode, just add a tag called release, and it should override that. And we'll test it with the max number range. And as you can see, the proof time took about 1.44 seconds, and the verify took about 1.19 millisecond. And last but not least, we're also going to check with the range, the over the range part, which would look something like this. All right, I just want to make sure if there's any questions. Can a custom range be used? Yeah, honestly, like these are custom range. I'm just using Mercine 31, or I'm only using like Baby Bear range check for example purposes. Like you can build your own custom range check, I guess, constraints if you want to. I hope that's your question. Or are you using custom range for Plonky 3 backend? If that's the case, there's only a couple of fields that we support. Like these are the fields that we support that you can plug it into a Plonky 3 backend. So those are slightly different. Okay. All right. So last but not least, we talked about the Baby Bear V1 range check. We're gonna skip the Goldilocks V1 range check, but it's pretty much very similar to the Baby Bear V1 range check example. So if you want to take a look, you can take a look at it. Take a look at the source code. This one has an even worse optimization. So now we'll talk about the V2 of Baby Bear range check and how to actually improve your constraints, right? How to make it more efficient. So V2 introduced an optimized version with reduced constraint degree. And so first, let's dive into the constraint degree. What is a constraint degree, right? So the degree of constraint in zero-knowledge proof refers to the highest degree of any polynomial constraint in the system. This is a very abstract way of saying it, but like I mentioned, it's basically in your polynomial, in your constraint that you have written, what is the highest degree of of your variables that exist. If there's multiplications of, let's say, I have a column and I use that column to multiply itself by 4 times, which will look something like x to the 4, x to the 4. which will translate to degree 4. And if I multiply multiple columns, like let's say 4 columns or 5 columns to one another, so column 0 multiply column 1, multiply column 2, multiply column 3 and 4, then that one means it's going to be degree 5. So yeah, that's what degree is at least in Plonky 3's constraints. Right. So how does the degree affects the proof generation process, right? The lower degree constraints generally leads to faster proof generation and smaller proof sizes as well. So this is because the prover and the verifier will need to perform fewer operations to verify the proof. And what's the relation between the blowout factor that I talked about versus the degree, right? So degree, let's represent the degree in D, which will lead to a blowout factor by the next part of 2. So D minus 1. So let's say my degree is 4, then the blowout factor is going to be 2. If my degree is 5, and in order to house degree 5, 2 to the 2 is equal to 4. It's less than 5. So it has to be 2 to the 3, which is 8. So 8 is more than degree 5. That's why for blowout factor, for degree 5 constraints, your blowout factor has to be 3. So on and so forth. And if there's like a degree 9, which will result in blowout factor of 4, because it's going to be 2 to the 4, which is 16. 16 is more than 9. Yeah. So yeah, our goal in writing constraints and to really optimize it, the idea is to try to reduce the constraint, the degree as much as possible, so that we don't have to increase the blowout factors. We try to keep the blowout factor as small as possible. I think for SP1 ZKVM, they kept their entire blowout factor to 2 for their massive constraints that they have written. So there's a lot of optimizations they have done, and that's also one of the main reasons they're so fast. So yeah, just an example, like I mentioned, for the same column, if you multiply yourself by 4 times, the constraint will be degree 4 and result in 2x blow up. And then if it's 5 columns multiplying one another, degree 5, which will result in 3 blowups. Right. So let's diagnose the problem in Baby Bear V1. Why is Baby Bear V1 constraint degree 4, and also why it has to have a blowout factor of 2? It's because of this line, this product where we're multiplying column 1 all the way to column 4. So there's 4 columns multiplying one another, which made which caused a problem. So the blowout factor has to increase to 2. And in V2, what we're doing is we're using this idea called intermediate representation, intermediate variable. It's basically relying on values from external, outside of the constraint, but we verify that the value provided outside is correct in the circuits, in the constraints, and then start using it, so that we're not using columns to doing the multiplication. Instead, we're using public values to doing the multiplication. So that's what intermediate variable is. So yeah, so let's dive into the process. So first thing, is very similar to the original Baby Bear V1. The first step and some of the third and fourth and fifth, they're all the same. The only difference is the multiplication part that we did. So first we need to check whether the most significant bit is 0. And then we'll talk about the second in a bit. But let's say if from column 1 to column 4 they're all 1, then the sum of the remaining columns should all be 0. So this condition still applies. And we're also checking every bit is either 0 or 1. And also we are reconstructing the values to match the inputs. So now this is the hard part, right? Or wordy part, but it's not very complicated actually. So what we're doing is we're gonna check every bits by bits. So we're gonna check the very last bits first. So check if the product of bits 3 and 4 is 1, right? So what it's doing is First, we're going to provide an external constraint input called A, and which we pre-computed the product of bits 3 and 4 outside of the constraint. And we're providing the pre-computed result as the public inputs, just like how we're providing the reconstructed value, the original value via the public inputs. We're also providing the products of bits 3 and 4 from public. So yeah, provide an external constraint input A, that is a product of bits 3 and 4. And what we're going to be doing, we're going to reconstruct the product in the constraints. So what we're going to be doing is we're multiplying bits 3 and 4 column in the constraint, and then we're going to compare if the reconstructed value is the same as the publicly provided value A, right? And compare the product with A. This step is to ensure A is correct. So if this passes, which means A is indeed, this A, which is the public value, is indeed the same as the product of column 3 and column 4. So let's keep that in mind. And secondly, what we're going to do is we're going to check if the product of the bits 2 to 4 is 1. So provide an external constraint input B, that is the product of bits 2, 3, and 4. If you can recall, oh, it's way too up there. I'm just going to do a screenshot so that it's probably better. Yep. All right, I'm just going to put it up here. So in the first step, remember, what we're doing is we're multiplying 3 and 4 and then compare whether public input A is equal to the product of 3 and 4. And now in the second step here, what we're doing is we're providing an external computed product, which is the product of 2, 3, and 4. We pre-compute that externally. And we're going to also do a reconstruction of the value in the constraint. But this time, instead of multiplying column 2, 3, and 4, what we're going to be doing is, because we have verified the product of 3 and 4, which is A, is correct. So instead of multiplying 2, 3, and 4, which is going to make the degree into 3, what we're doing is we're multiplying column 2 to the product A, the public value A, which is going to keep the constraint degree into 1. So we have reconstructed the value by multiplying 2 to A, and then we can verify whether B is correct or not. And B is the publicly computed product of 2, 3, and 4. And we're going to do the same exact thing, and we call that a C. And C is basically a product of column 1, 2, 3, and 4. And with 1, 2, 3, and 4 that provided publicly, and we're going to reconstruct the value by multiplying the column 1 to the publicly provided value B, which is the representation of 2, 3, and 4. And if it passes, then C is going to be correct, right? And C correct as in like C is indeed a representation of the multiplication of column 1, 2, 3, and 4. And by doing so, we kept the degree down to 2. And last but not least, we're going to check whether if C is equal to 1 or 0. Right? If it's 1, then the remaining bits must be 0. If it's 0, then remaining bit can't be anything. Right? So this is how we override, or I guess like overcome this like degree problem by relying on public inputs, which we call intermediate variables. And we make sure the public inputs that's provided is indeed correct. And we make sure it's correct via doing it in the constraints. And once they're correct, we can use them as a source of truths that we can rely on. And we do the additional computations on top of the public inputs. All right, so let's dive into the code. So this is the constraints. And as you can see, we have provided various public inputs, which this is to compare with the reconstructed value. And these are basically the representations of, the most significant bits of, this is the value A, this is the value B, this is the value C, right? And this is the width. And the only thing that we need to change is this part here compared to the V1. So first, we also need to check the most significant bits is 0. So this has to pass. And then what we're doing, we're going to check whether if value A, the publicly provided value A, is indeed the product of column 3 and column 4, column 4 and column 3. If it passes, then we're going to check the value B. And we're going to check it with the value A together. Say, this is the publicly provided value B, and then we're going to convert this value B into a field expression, and this is what it's doing, right? And then this is where we're going to compute with the publicly provided value A. So A multiply column 2, and then you compare. If it passes, then we go on and compute the C, and then make sure C is also correct as well in here. And last but not least, if C is equal to 1, right, using this when API that we mentioned, if it's equal to 1, then it's going to run this assert 0. If not, it's not going to run. All right, and then reconstruct the value, etc., and then check whether the reconstructed value is equal to the original value. That's the same thing that we have done 3 times. All right. And slight changes, I guess, I just added here, but, the execution trace that we're making, execution trace is the same. It's the same as before. But I guess I'm just showcasing what we're doing externally by providing the public inputs. I guess this is the bits, you're comparing, you're multiplying the 4th bits and the 3rd bits, all that, and then you're providing it for your circuits. Yep, and prove and verify. And what we need to be mindful of here is because we have optimized the constraints, and the biggest degree that we have in our constraint is 2, so we can reduce the log blowout degree down to 1 instead of 2 from the original example. Yeah, and I guess this is just some of the inputs. So yeah. So I guess that's about it for the range check example. Range checks are essential components in zero-knowledge proof systems. Yada yada, just a lot of stuff. Just read it. But yeah, it's very important. I totally recommend to check out this repo. And then I have leave this sort of a question mark here, where if you want to challenge yourself, you can try to build your own Goldilocks V2 range check. Which the V1 version is just like the Goldilocks V1 version is just like Baby Bear V1, and it's even worse of an optimization. It needs an intense optimizations to be done. So if you want to take the challenge and you want to work on it, feel free to work on it and then create a PR, and would love to add your implementations to this tutorial for others. But yeah. I guess that's about it for the range check example. Let's see if there's any questions. There is some renewed concern around quantum computing and existing cryptography as Plonky 3 is. No, it's hash based, it's Stark, so not really. But yeah, I do see where that's coming from. I think it was Google, they announced it yesterday, no?
Thank you, Brian. I'm back. There was also some discussion about kind of the origins, really, of Plonky 3. So I don't know. Yeah, I don't know if you know about this, but yeah, we had discussion from Anna, and actually the question from Let's Try Hard. Did Aztec make Plonky 3? So I think there are maybe some confusion about Plonkish. Plonky.
Oh.
So what's your take on
Plonkish, Plonk, all that. It's so Plonk is Aztec, right? Plonkish is like Halo 2, all that. And then Plonky 2 is so Plonkish is sort of an optimization, that kind of a scheme. And how do I compare? So Plonk is sort of a constraint system, basically, right? We talked about air in Plonky 3 a lot. The name is confusing, but Plonky 3 doesn't use Plonk. It doesn't use Plonkish, right? Plonky 3 uses air, and it uses, all the Stark and all that stuff. Whereas, Plonk, if you want to compare Plonk, it's a constraint system. You can compare Plonk to, R1CS. You can compare it to air. You can compare it to, there's another thing called CCS, which is like, so overall, I think CCS is sort of like overall representation that you can convert CCS into Plonk. You can convert CCS into R1CS. You can convert CCS into air. I think that's what CCS is. I don't know too much about it. But yeah, these are constraints. So that's what Plonk sits in. It's sort of in that scope. Plonkish is more so of, I don't know Plonkish that well, but it's sort of an arithmetization process, which is, if you have constraints, then you're converting your constraints into, with the execution tree, you're converting into this polynomial process. And I think that's where it sits in. So that's Plonkish. The name sounds confusing, but they're actually a little bit different. Like they don't serve the same similar purpose, and they're not.
There was actually a whole discussion in the YouTube comments as you were speaking. So I actually invite people who watch the recording of this to actually check out the comments on YouTube. That's gonna be probably the best way to get to the bottom of it.
Yeah.
And maybe the last questions before we close the workshop is from Rocio. So she's asking, I'm new to Plonky. How do I get started? So is actually your repo that you shared maybe the best place to start with, or there is something maybe a bit?
Yeah. So for us, because Plonky 3, honestly, we encourage a lot. We encourage people to build on top of Plonky 3, but we also ask them the question too. It's like, hey, it's Plonky. Do you really need? What are you trying to build? Are you trying to build a simple ZK VM system? Are you trying to build a simple ZK program? Then maybe using something like ZK VM will be faster than learning a whole ZK backend. But if you do know that you do need to use Plonky 3, then you're at the right place. So some of these tutorials that I talked about, the Fibonacci example and the range check that I just shared you, and also if you go to the Plonky 3 repo itself, we have a couple of examples. Okay. I think we recently also added this Blake 3 air example. So we have 3 examples of hash functions: the Blake 3, the cat air, and also the Poseidon 2 air. Right? If you just search -air, then you'll be able to see here's one example. Here's the second example, and this is the third example. So you can take a look at how we write constraints, and then also how you can convert those constraints into different Plonky 3 settings to get started. But next year, early next year, we are also, I'm currently working on it. We're gonna have a sort of a Plonky 3 0 to hero series. And these 2 that you saw, the Fibonacci and range check, are it's going to be the very first 2 chapters. And then we're going to have the lookup tables, static lookup tables, the dynamic lookup tables, etc. To implement it so that you have a sort of a full range of, from beginner to all the way to, sufficient Plonky 3 developer experience using that one tutorial repo. So that's coming along, but I don't have a good timeline for you yet because right now we focus more on ACLAIR as well. So, but that's definitely going to come along. I hear you. We're going to make it as fast as possible.
Yeah, so we shared already the links to this repo that you presented today in the workshop in the YouTube comments. We will share some more info, so people are asking also where to follow you on X and all. So we will share all this information, extra information in the Discord. So I can see people asking who are already there. But again, if you're watching the recording afterwards, feel free to hit us up in there. Okay, I think we have Anna.
Sorry, I just did a share screen, share slides, did not realize it was going to pop right onto the screen.
Yeah, it was hidden.
I'm still actually looking for Kobe in the backstage. So Gaylord, I don't know if you want to go help me find him.
Yeah, yeah.
Brian, thank you
fire
so much
Brian.
for this workshop.
Yeah, thanks for the opportunity, you know.
Yeah, it was wonderful. And
Yeah,
yeah,
thank you very much, Brian.
very nice.
Cool.
I know that there's still a few kind of questions in the chat. So if you can just maybe head over there after and just like answer for folks if they're looking
Okay.
at links and stuff like that.
How do I answer? Mind me ask?
Oh, just head over to the YouTube video.
YouTube. Okay.
Yeah, I sent it to you right now. It's so that you can.
All right. I'll do that.
I think we covered pretty almost all the questions, but yeah, if you can see anything, feel free to jump in there. That's useful because typically when people will watch the recording afterwards, the comments are actually still popping up. So that's
Right.
quite nice to have this all sorted right now.
Perfect. Yeah. Thanks so much.
Sure.
Sounds
Thanks,
good.
Brian. Thank you.
Cool.
Bye-bye.
All right. So yeah, Gaylord, thank you for hosting this one. I know you're going to head now into the backstage in order to get the puzzle ready to go.
Yeah,
I
the
just
puzzle
hope
is almost ready to go. I need to tweak a couple things, and then we will release it. But I guess before that, yeah, you will introduce that.
Yeah. I have a few slides. I'm just sort of like so far we need to make sure someone from the team is here to help us describe this puzzle because I will not be able to.
Yes.
Yeah.
I will try to track them down, and in the meantime, yeah, I'll let you introduce the freebies that you have in your slides. So see you in a bit.
Good. Cool. All right. So yeah, we are now just kind of wrapping up the third session of ZK Hack 5, session 3. Yeah, so what we've been through today is we kind of announced the V-2 winners. We just heard the workshop from Brian. And yeah, we're meant to now launch in 4 minutes Puzzle V3. And usually we have some explanation. So hopefully we can find someone to join us to share that. Otherwise, we're going in blind, I guess. I think we can still release it. It's just there will be no hint. Anyway, okay. I want to say a big thank you to the partners for ZK Hack 5. A lot of some of these folks have come back. Some of them we know them from other events, but thanks to the main partners, ZK Verify, Nebra, and Polygon, who we heard from today. We also have our community sponsors, Zion, ZK Pass, Firma, and Powder. All 7 of these you'll hopefully be meeting next week at the job fair. We're going to encourage everyone to come out. Every one of them has a booth. Some of them are hiring. Not everyone is hiring, but we do think of the job fair also as like just a chance to get to know each other. So it's also fun if you just want to meet these teams. Maybe you want to collaborate with them. Maybe you just want to, find out what's on their minds. As always, the media partner is the other kind of entity you might know me from, the ZK podcast. And like this time around, we're doing all of the videos over on the ZK Hack YouTube channel, but you'll see kind of the job fair is hosted on the ZK podcast website. And we're kind of sharing in terms of, just sharing a lot of the marketing and getting the word out. Okay. So yeah, and this is where you've been probably watching us over on the YouTube channel. Yeah, I'm a little, so we have 2 minutes, but so far I see no bug in the background. And so I'm sort of not sure what I'm supposed to do here. Okay. Apparently he's coming. I think he's coming. Oh wait, okay. I think I wonder if okay, let's see what we got. I think we might have something happening. Yes, like always, find us on the Discord, follow us on Twitter. Once again, thank you to the team. Like this was put together really by Gaylord, Quenta, and myself. And then the puzzles were put together by Kobe, Andrea, and Nico, as well as other members of the team over there. So yeah, thanks to everyone who came out. And I do see someone in the background. It's just a familiar face this time around. We're gonna bring him back to the stage just in time. Hey,
Hello.
have we seen this bug before, perhaps?
Yes.
Did you
I
run
haven't had a chance to get a new bug face, so I'm using my current regeneration for this bug. So
I see. Well, it's great to have you here. I was trying to figure out
yeah,
how to
thank
sort
you
of
for
like
covering.
song and dance my way through this launch. But
Thank
okay,
you.
cool. I'm so glad you're here. Tell us a little bit about V3. This is our last
Yes.
puzzle of ZK Hack 5, by the way, folks. So yeah, I'm very excited to hear about it.
Yes. So this puzzle is called Shadow, or what lurks in the darkness. And when you solve the puzzle, you might understand why. But generally, we wanted to spice up things and kind of show how new tools, or tools that are becoming more and more popular, also have bugs. That happens, or can be misused, or can be used in different ways. So what we chose to use this time is Noir. And specifically, this is a puzzle that is inspired by Aptos Keyless and ZK email. So this is another topic that has been very hot and important in the last year, around how to import Web2 identities into Web3 or crypto. And this is a puzzle that shows what can go wrong when you do this. And it was inspired by these projects because these are things that these projects encountered in their past.
Well, I just saw, I don't know, Gaylord, do you want to just jump on? Because I think this may be live. Is it live? Oh, you're muted. You're muted.
Sorry, yeah, I always do that. It's excitement of releasing a puzzle. Always do that. Yeah, it's live. Check it out. It's available. So you have the page, the dedicated page. I just posted the link in
Saw
the
that.
YouTube comments, and
Right on the hour.
Exactly, right on the hour. I'm personally very excited to see people, also discovering Noir if they haven't used it before. It's a change. I think from what I've seen, most of the puzzles were done in Rust, so it's fun to, as Kobe said, to experiment also with up and coming languages. So I'm very excited about this one too.
Yeah. So just like one other note, this puzzle, has been built by the people that you already know, but also Gersta this time.
Oh yeah.
She actually worked on a few things in that area of Noir and related topics. So this is also a work that is inspired by her recent work.
Amazing.
And yeah, and we've been collaborating and doing all of this puzzle in Noir for the benefit of everyone here. So
cool.
Have fun.
Yeah, and I feel like there's already some folks who've seen the link, they've bounced off, ready to do it. I think we always share this. There's a bit of some deadline timing. We had some people come in really right under or even after the wire this time around, right?
Yep.
The way it works is this is going to be running for a week until Monday, December 16th at 11:59 p.m. So this is midnight, just so it's clear. I know that sometimes people are submitting after the fact, but before we announce the answer. And in that window, we will still list them on the leaderboard, but they'll just have 0 points. And it is kind of cumulative, but it's still awesome to see new names pop up there. So, even if you're right down to the wire right after, you can still submit it. But this is, if you want to get points, you have to submit it. And this time, I know there's some people who go really fast. I'm so curious because the first puzzle took a long time for people to the first people, I think it took 4 hours or something. Yeah, which is very unlike, sometimes these are a lot faster. And then the last one was faster.
Yeah, the first one, actually, I didn't mention before, but it was 13 minutes and 44 seconds for the fastest, which is
one.
Quite insane. Yeah, the second one. This one, I don't know.
Yeah.
I don't think after 4 minutes we have any successful submission. I hope that. I suspect the fact that it's in noir might make things a bit different as well. So yeah, I'm curious to see how it reshuffle or not the leaderboard.
Amazing.
Yeah, and if you encounter some more problems, like feel free to ask in the chat. There are some Aztec people around, so
Amazing. Cool. Next week on the 17th, so that's the day after it's due, we're going to be sharing the Puzzle V3 winner announcement. So that will just be for this past week. We have our fourth session, third workshop with Shumo from Nebra. And once that's over, we're going to be doing the closing prize ceremony. So this is where we're actually going to be giving out prizes. For anyone who's won already, this is something we forgot to mention, is like we're going to do all the payouts also at that point. So you'll be seeing that. We're going to be kind of chasing you a little bit for Ethereum addresses and just generally addresses so that we can make sure that we can give you your prizes. So just be aware of that too. I almost think if you're already ranking, you might want to let us know in advance if you want. But yeah, so we're going to be announcing all of our top winners. We have some wonderful prizes coming. I sort of hinted at them. They involve some travel, some exposure, some objects of various sizes that we're going to be shipping around. So yeah, some fun swag. After that, next week, as Gaylord mentioned earlier, we're going to be hosting our virtual ZK Jobs Fair. This is probably like the 10th time or so that we host this kind of event. And this picture doesn't fully do justice to it. What you get is like a little avatar, like a little character, and you can walk around this digital space and you can walk up to people. And when you walk up to them, both videos turn on. And then when you walk away from them, the videos disappear, kind of fade out. And it's a really nice way to get to know the people who participated, people in the community. And also, obviously, if you're looking for a job or you're looking to just connect with some of the projects here, this is a good chance to get to know them. You can do it from the comfort of your home. You could kind of like meet them just for like 5 minutes instead of setting up a full appointment. So this is sort of like a nice and easy way for you to get to know a lot of people. There have been some great hires that have come through this too. We've been collecting some of the sort of testimonials of the job board and the job fair. But I mean, we know some folks, and maybe even we'll meet some folks next week who've kind of gotten their jobs or their starts through this jobs fair years ago. So yeah, anyway, really good. Really excited to do that again. And I think that's the end. Of all of our links. I think we've shared them a bunch of times in the chat. Big thank you to everyone who came out for our third session. And yeah, next week is our finale, and then we will be wrapping up ZK Hack 5, but we still have this last puzzle, and yeah, we have some fun coming. So
have fun.
Thanks a lot.
Thanks. Bye, guys.